The sound you hear is that of an extremely worn pump bearing. Most mechanics will agree that when a bearing sounds this bad, it'll need to be replaced soon. Although most bearings do wear out eventually, in many cases, a bearing may wear out prematurely, which means that the equipment involved will require maintenance more often than it should. Bearing wear can be attributed to many factors, including improper lubrication or cooling. However, another factor that contributes to premature bearing wear is shaft misalignment. When a motor or other driver is coupled to a piece of rotating equipment, such as a pump, the shafts of both components need to be aligned so that the center line of each shaft is in the same line, similar to what we've illustrated here. When two shafts are misaligned, that is, when their center lines aren't in the same line, excessive vibration and equipment wear can occur. Either of these conditions can lead to premature equipment failure and extra maintenance time. Mechanics like yourself are generally responsible for aligning the shafts of rotating equipment. In order to do the job properly, you'll need to know the tools involved and how alignment procedures are performed, as well as what's actually taking place when shaft misalignment is measured and corrected. And there can be several reasons for performing a shaft alignment. For example, when a driver or piece of driven equipment is removed for repairs, the shafts will have to be aligned after it's reinstalled. Or if excessive vibration is detected in rotating equipment, the alignment may be checked to see if shaft misalignment is causing the vibration. Your facility probably has policies that cover alignment procedures for different situations. However, in this program, we're going to look at some of the aspects of shaft alignment involving equipment that has been reinstalled, since that's probably the most common reason for an alignment. We'll discuss alignment theory, the different types of misalignment, how they're measured, and how they're corrected. We'll also discuss what's involved in preparing for an alignment. And finally, we'll look at one method of shaft alignment called the rim and face method. For the remainder of this part of the program, though, let's focus on alignment theory. We'll begin by discussing the different types of misalignment, and we'll use a simple illustration to help you better understand the concepts involved. When two shafts are aligned, their center lines are in the same line, or collinear, as it is commonly referred to. Now, there are two primary types of misalignment: parallel misalignment and angular misalignment. Parallel misalignment means that the two shafts are offset, like the example you see here. If we show the center lines of both shafts, you can see that they are not collinear, but they are parallel. Angular misalignment can be illustrated in a similar fashion. As you can see, they're not collinear. Instead, the center lines intersect at an angle. Now, in addition to there being parallel and angular misalignment, these types of misalignment can be present in a vertical and a horizontal plane. Let's take a moment to illustrate this point. When looking at the end of a shaft, the vertical plane is above and below the shaft. The horizontal plane, on the other hand, is to the right and left of the shaft. In order to see misalignment in the vertical plane, we'll have to look at the shafts from the side. As this side view shows, parallel misalignment in the vertical plane looks like this. The center lines of the shafts are parallel, but not collinear. Angular misalignment in the vertical plane looks like this. The center lines of the shafts are not parallel or collinear, but intersect at an angle. In order to see misalignment in the horizontal plane, we'll have to look at the shafts from a top view. In the horizontal plane, parallel misalignment looks like this, and angular misalignment in the horizontal plane looks like this. In addition to what we've seen so far, it's possible for two shafts to have combined misalignment. That is, a combination of parallel and angular misalignment in both the horizontal and vertical planes. To see this, we'll have to look at the situation from two different views. Here, we're looking at the shafts from the side, so we'll be looking at misalignment in the vertical plane. As you can see, when we extend the center lines, the shafts are parallel misaligned, but there is no angular misalignment. Since we can't determine if there's any misalignment in the horizontal plane from this view, let's look at the same situation from a top view. From this view, we can look at misalignment in the horizontal plane. When we extend the center lines of the shafts, we find that they are angular misaligned. In addition, notice that it is impossible to see the misalignment in the vertical plane from this view. So even though there are two primary types of shaft misalignment, parallel and angular, they can occur in the vertical or horizontal plane or in both, and you'll have to look at both planes to determine the actual misalignment. Well, we've discussed some of the basic aspects of alignment theory. We discussed what shaft alignment is and what it means when two shafts are misaligned. We also saw what parallel and angular misalignment look like in both the vertical and horizontal plane. In the next part of the program, we'll continue with some additional information about alignment theory that you'll need to be familiar with in order to perform an alignment. In the last part of the program, we introduced you to some of the basic concepts of alignment theory. We discussed what it means when we say two shafts are aligned and the different types of misalignment that can be present between two shafts. In this part of the program, we'll use that information to see the basic principles involved in measuring parallel and angular misalignment. Then we'll take a basic look at how shaft misalignment is corrected. A vital part of shaft alignment is establishing reference points and keeping them the same throughout the alignment procedure. If you change your reference points during the alignment, chances are that the shafts wouldn't be aligned when you're done. One reference point you'll need to establish is your orientation in relation to the equipment. There are a few terms we'll need to define in order to explain how it's done. Although you're likely to find many different combinations of drivers and driven equipment, a common situation involves a motor and a pump. So we'll use them as an example in this program. The first two terms we need to define are the movable component and the fixed component. The movable component is defined as the component that will be moved in order to align the shafts of both components. Generally, the movable component is the one that is easier to move. Because pumps are connected to piping that makes them difficult to move, motors are usually chosen as the movable component. The fixed component, then, is the component that is not moved. It remains stationary, and its shaft becomes the reference that is aligned to. Since pumps are generally more difficult to move, they're usually chosen as the fixed component. To properly orient yourself, you should be in a position where the fixed component, in this case the pump, is on your left, and the movable component, in this case the motor, is on your right. Now, because we're concerned with misalignment in both the vertical and horizontal planes, there's another part of this orientation that you'll need to be familiar with. To explain this part, let's look at the hub of the fixed component. As we pointed out earlier, the vertical plane is above and below the shaft, while the horizontal plane is to the right and left of the shaft. If we think of the hub of the fixed component as a clock face and put on markings for 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock, 12 and 6 o'clock would represent the vertical plane, and 3 and 9 o'clock would represent the horizontal plane. Using this orientation consistently is important in doing an alignment correctly because it makes keeping track of what the misalignment measurements mean much easier. Now let's take some time to discuss what's being measured when we measure misalignment. In this illustration, we've exaggerated misalignment in the vertical plane to be able to see it more clearly. By looking at the illustration, you can see that the hub of the movable component is offset towards the 6 o'clock direction. It's this offset that must be measured to determine how much parallel misalignment in the vertical plane exists. You'll also notice that the gap between the two hubs is wider at the 12 o'clock position than at the 6 o'clock position. This difference is what we'll have to measure to determine the amount of angular misalignment in the vertical plane. Now, if we change our vantage point and look at this illustration from the top, you can see that the hub of the movable component is offset towards the 3 o'clock position of the fixed component hub. This offset must be measured to determine how much parallel misalignment there is in the horizontal plane. You can also see that the gap between the hubs is wider at the 3 o'clock position than at the 9 o'clock position. We'll measure this difference to determine the amount of angular misalignment in the horizontal plane. Now, let's take a moment now to look at what's involved in shifting the movable component so that the shafts are in alignment. Correcting for misalignment in the vertical plane involves adding or removing shims under the feet of the movable component. For parallel misalignment in the vertical plane, the same amount of shims will be added or removed under each foot of the movable component. However, when correcting for angular misalignment in the vertical plane, different amounts of shims will have to be added or removed under the feet of the movable component. For example, in this illustration, we'd have to add more shims under the feet at this end than at the other end to correct the angular misalignment. Correcting for parallel misalignment in the horizontal plane involves shifting the movable component in either the 3 or 9 o'clock direction. In this example, the motor must be shifted towards 9 o'clock in order to correct for the parallel misalignment. To correct for angular misalignment in the horizontal plane, the movable component must be shifted in a similar manner. In this example, both ends need to be shifted towards 3 o'clock. However, this end must be moved more than the other end to correct for the angular misalignment. By now, you should have an understanding of the theory behind shaft alignment and the basics of measuring and correcting for parallel and angular misalignment in both the vertical and horizontal planes. In the next part of the program, we'll begin looking at some of the things that must be done before performing a shaft alignment. Before actually performing a shaft alignment, there are some preparations that you should make. During the next 2 parts of this program, we'll discuss these preparations and see how they're performed. Now, not all of these preparations have a direct impact on performing an alignment correctly. However, they're usually included as part of an alignment procedure. One of the first preparations that must be made is to make sure that the pump and motor are isolated and tagged out. Having the equipment start up while you're performing an alignment could seriously injure you. Another preparation involves inspecting the foundation or bed plate that supports the pump and the motor. The foundation should be checked with a bubble level to ensure that it's level. If it isn't, you'll have to verify that the fixed component has been shimmed to make it level. You can check this by placing the bubble level on the shaft or other horizontal surface of the fixed component. If the foundation is concrete or grouted, you'll need to make sure that there are no cracks or loose material that will create an unstable platform for the equipment. It's also a good idea to check the mounting bolts for the equipment. They should be tight, and the bolt anchors should be securely set in the foundation. In addition, the surface of the foundation where the movable component sits should be clean. You'll need to remove any corrosion, paint, or anything else that would interfere with the frame sitting solidly on the foundation. The seating surface should also be stoned to remove any nicks, burrs, or other raised imperfections. Additionally, each foot of the motor should be cleaned and stoned to make sure the motor sits solidly on the foundation. Now, the rest of the preparations we'll be discussing in this part of the program involve dial indicators. So let's take some time to discuss them before we continue with the preparations. There are 2 types of dial indicators typically used for alignment work. The one you see here is called a balanced type. It has a face which is graduated in thousandths of an inch, or mils. It's operated by a plunger or stem that moves the hand on the face. Inward movement of the stem moves the hand in a clockwise or positive direction. Outward movement of the stem moves the hand counterclockwise in a negative direction. You'll also notice that the face can be rotated in order to set the reading to 0 with the stem in any position. This type of dial indicator is used primarily for measuring the misalignment between 2 shafts, which we'll see a little later in the program. The other type of dial indicator used in alignment work is called a continuous type. Its face is also graduated in mils. However, the increments on this one go from 0 to 100 mils. This larger needle indicates stem travel in 1 mil increments between 0 and 100 mils. There's also a smaller needle that indicates stem travel in increments of 100 mils. This arrangement makes it easier to read measurements over 100 mils. Like the balance type, the face on this dial indicator can be rotated to obtain a 0 indication with the stem in any position. You'll notice, however, that the small needle always indicates the amount of stem travel regardless of where the face is zeroed. The next preparation we're going to discuss involves the use of continuous type dial indicators. It's called checking for pipe strain. Pipe strain is the force exerted on the fixed component from suction and discharge piping that is not supported properly. This force, if not corrected, could make it difficult to properly align the shafts. One method of measuring pipe strain involves mounting two dial indicators so that their stems contact the rim of the fixed component's hub. One of the dial indicators is mounted at 12 o'clock and the other is mounted at 3 o'clock. Attaching the dial indicators in this manner allows pipe strain to be measured in the vertical and horizontal plane. Next, each dial indicator is adjusted for a zero reading. At this point, we'll have to loosen the suction and discharge pipe flanges. This will relieve any pipe strain that may have been present. Then the dial indicators are checked. Any reading other than zero on the indicators means that the fixed component moved because of pipe strain. Your facility probably has set limits for the amount of pipe strain that is allowable. In some facilities, the rule of thumb is that any dial indicator reading of more than 2 mils must be corrected. In order to correct pipe strain, adjustments in the piping supports will have to be made. Pipe hangers and supports may have to be moved in order to eliminate pipe strain. Once the adjustments have been made, the procedure we just saw would have to be repeated to see if the pipe strain has been corrected. The next preparation we're going to discuss is checking for a soft foot condition. A soft foot condition exists when one or more of the movable component's feet are in different planes. When this condition is present, the motor housing will twist when the support bolts are torqued down, which can make it difficult to properly align the shafts. To check for a soft foot condition, it's necessary to tighten all of the support bolts on the movable component. Then a dial indicator is mounted to indicate vertical movement of one of the feet and is adjusted to read 0. Next, the support bolt is loosened and the reading on the dial indicator is recorded. Any reading other than 0 indicates a soft foot. Most facilities have set limits for the amount of movement that is allowable. In this example, any soft foot condition more than 2 mils must be corrected. To correct a soft foot condition, a shim, the same size as the dial indicator reading, must be inserted under the soft foot. Now the support bolt is retightened and the same steps will have to be repeated for each of the remaining feet. The number of soft feet can vary. In some cases, only 1 foot may be soft. However, it may be necessary to shim 2 or 3 soft feet in some situations. Once all the feet have been checked, it's a good idea to recheck each foot to verify that the soft foot condition has been corrected. Another preparation that should be made is to take run-out readings. This involves measuring the run-out of both the fixed and the movable components. Excessive run-out on either component will make it nearly impossible to correctly align the shafts. If you're not familiar with taking run-out readings, we've included the details on how they're obtained in your text. Although the preparations we've been discussing in this part of the program have focused on either the fixed component or the movable component, some situations may require that these preparations be performed on both components. The methods we've shown here can be used for either component. Let's pause now to give you a chance to review the information that we've talked about in your text. When we continue, we'll look at some additional preparations that should be made before performing an alignment. In the last part of the program, we looked at some of the preparations that are generally made before performing a shaft alignment. We discussed inspecting the foundation, the mounting base, and the motor feet. We also looked at what's involved in checking for pipe strain and soft foot. In this part of the program, we'll continue our discussion on preparing for an alignment. One preparation that's generally made prior to performing a shaft alignment is determining the thermal growth characteristics of both the fixed and the movable components. Thermal growth is a term used to describe the physical movement that occurs as a piece of rotating equipment reaches its normal operating temperature. Different types of rotating equipment have different thermal growth characteristics. For example, when a motor is started up, it produces heat. This heat causes the motor housing to expand, which in turn causes the shaft to rise slightly. On the other hand, a pump that pumps cold liquid has a different thermal growth characteristic. In this situation, the cold liquid passing through the pump causes the pump housing to contract. This then causes the shaft to lower slightly. For that reason, the thermal growth characteristics of both the fixed and the movable components must be determined and taken into account when performing an alignment. Some equipment manufacturers determine the thermal growth characteristics for their products, so you may be able to find this information by checking the equipment manuals for the components you'll be aligning. However, if this information isn't available, it may be necessary to measure the actual thermal growth of the components. Your facility may have procedures on how thermal growth is measured. You'll also find descriptions of a couple of ways of doing it in your text. Up to this point, we've discussed most of the preparations that are made before performing an alignment. The order in which you perform these preparations hasn't been critical so far. However, the last preparation we'll discuss should be the last one done before actually aligning the shafts. It's called setting the face gap of the hubs. Most couplings are designed to operate with a specified amount of space or gap between the faces of the hubs. The purpose of the face gap is to prevent damage to the hubs and coupling from axial movements of the shafts. The term axial movement refers to the amount of movement back and forth that is allowed by the bearings that support the shafts. If the face gap is too narrow, axial movement may cause the two hubs to contact each other and become damaged. On the other hand, if the face gap is too wide, the coupling may separate and be damaged. You'll need to check the coupling manufacturer's specifications to determine the gap that's required for the particular coupling you're using. For example, these specifications show that this hub should have a minimum gap of 1/16 inch, or 62.5 mils. The maximum gap for this hub is 5/32 of an inch, or 156 1/4 mils. You'll also notice that the ideal or normal gap for this hub is 1/8 inch, or 125 mils. With the gap set at 125 mils, the coupling should be able to handle axial movement of the two shafts without damage. In order to set the face gap, the motor must be moved into position. It's a good idea to eyeball the two hubs to get them reasonably close to being aligned while adjusting the coupling face gap. This will make it easier to take misalignment readings later on. Many mechanics will use a straight edge and feeler gauges at this stage to get the two shafts close to proper alignment. Now, you'll need to get a feeler gauge the size of the ideal face gap specification that was determined earlier and insert it between the two hubs. You may have to move the motor to get the face gap set to specifications. Finally, the motor support bolts should be tightened. Setting the face gap for that pump and motor was fairly easy because both components involved bearings that held the shafts in their normal operating position. So axial movement was minimal. However, when larger equipment is involved, particularly components that have sliding surface bearings, much more axial movement may occur. So in those situations, you may have to perform some additional steps before setting the face gap. One step you may have to perform is determining the mechanical center of the fixed component. That is, finding the normal operating position of its shaft. To determine the mechanical center of a pump, this mechanic first forces the pump shaft inward as far as it will go. Then a dial indicator is mounted so that its stem contacts the face of the pump's hub. And the dial indicator is adjusted for a 0 reading. Since the stem was partially compressed when the dial indicator was mounted, the small needle reads 1, meaning 100 mils, when it was zeroed. We'll need to keep this in mind when we take the final reading. Since we need to determine the total amount of axial shaft movement, the next step is to force the shaft outward as far as it will go. Next, the reading on the dial indicator is checked. In this case, the small needle reads 2, meaning that at least 100 mils of travel occurred. The large needle indicates 31.5, so the total travel was 131.5 mils. This reading is the total amount of axial shaft movement. To determine the mechanical center, we'd have to divide the reading by 2, which would be 65 3/4 mils in this example. After the mechanical center is determined, the shaft would have to be moved back inward half the total movement to set the pump shaft on its mechanical center. Then the face gap could be set to the ideal specification. Axial movement is present in motors just like any other piece of rotating equipment. However, because of the magnetic field that is created by the field windings in the motor, the rotor is held in the same position each time the motor is operating. This characteristic is referred to as the motor's magnetic center. Like mechanical center, you may have to determine the magnetic center of the motor before adjusting the coupling face gap. In some cases, the magnetic center for a motor is specified in the manufacturer's manual. However, if this information isn't available, it's possible to determine it while the motor is running. Before determining the magnetic center of a motor, you'll need to ensure that the motor is properly secured to prevent the motor from getting away from you when it's started. Here, the hub and coupling parts have been removed. If this isn't possible, loose coupling parts should be restrained so that they won't fly off when the motor's started. Now the motor can be started. As you can see, there's a great deal of axial movement as the motor comes up to speed. Once it's reached its normal operating speed, its magnetic center can be determined by first spraying the shaft with layout dye. Next, scribe a line on the shaft using the end bell or similar part of the motor as a reference point. When the motor is turned off, and this mark is lined up with the reference point, as it is here, it indicates that the motor shaft is at magnetic center. At that point, the face gap can be set to the ideal specification. For the remainder of the program, we'll be discussing one particular shaft alignment procedure, but you'll need to have a good understanding of the information we've covered up to this point before we continue. So let's pause for now to give you a chance to review this material in your text. Up to this point in the program, we've focused on the theory behind shaft alignment and the preparations that are necessary prior to actually performing an alignment. For the remainder of the program, we're going to be discussing one particular method of shaft alignment. It's called the rim and face method. Chances are that your facility uses this method for at least some of their alignment jobs. The rim and face method involves taking dial indicator readings, using formulas or graphs, and correcting the misalignment in the vertical and horizontal planes. In this part of the program, we'll concentrate on getting everything in order to begin the alignment. Then, in the remainder of the program, we'll look at what's involved in measuring and correcting misalignment using the rim and face method. As we pointed out earlier in the program, two types of misalignment can be present: parallel misalignment and angular misalignment. They can be present in both the vertical and horizontal planes. Parallel misalignment means that the two shafts are offset. Their center lines aren't collinear, but they are parallel. It's this offset that we'll have to measure to determine how much parallel misalignment is present. Angular misalignment means that the center lines of the two shafts intersect at an angle. The gap between the two hubs is larger on one side than on the opposite side. We'll have to measure the difference between the two sides to determine how much angular misalignment is present. To perform an alignment using the rim and face method, a couple of things need to be done. First, we'll need to be able to rotate both shafts. Here, the grid for this coupling has been installed to allow us to rotate both shafts at the same time. Secondly, dial indicators are mounted on brackets, similar to what you see here. In this setup, one bracket is attached to the shaft of the movable component, with two dial indicators mounted